In this video, I'd like to talk about this paper called Emerging Properties in Self-Supervised Vision Transformers, which they propose a novel self-supervised approach called DINO. And it's a very interesting line of research that, given an image without giving any single annotation, it somehow learns to give us a rich representation out of it that can be helpful for various vision tasks like classification, image retrieval, copy detection, you name it. We can see some of the samples on the first page of this paper that they drew an image with a self-attention coming out of the CLS token, which is a learnable token that we manually add as the input. If you forget or for some reason don't know what this token is, I highly recommend watching the Vision Transformer video. Anyway, as we see from the image of a jungle with a bird in it, the model throughout learning should learn that we only care about the objects in the image and only pays attention to the bird, or here to the toothbrush, here to the building, here to the giraffes, and so on and so forth. Or to show you even more examples, we can see an RGB video on the left and compare the attention coming out of a supervised method versus DINO. Clearly, we can see that the supervised approach that we explicitly give it a label that it must focus on, it focuses on the dog plus some areas of the background which are not very useful for our ultimate task. For example, if I want to detect the bounding box around the dog, knowing only the area where the dog exists should be more helpful. And we can see DINO that surprisingly, without even telling it where the dog is and where to focus on, throughout the whole video, it only pays attention to the dog. And to show you even more, we can see these four videos. One thing to note in these videos is that even when half of the ship is behind the sea or horse leg is below the grass, it is not problematic for DINO and it still can focus on the area of the interest. Or in ambiguous examples like here, when monkey goes out of the frame, it focuses on the tree branches as there is nothing else more important to focus. But as soon as the moment when monkey returns, it focuses on the monkey as it is more important for our vision tasks. And finally, we can see what happens on the feature space throughout training. Initially, as you can see, it is not possible to distinguish different classes of the images, but throughout the training, it learns a representation that at the end, each class is in different area of the feature space. That gives us the advantage of having something that even without a linear classifier and using a k-nearest neighbors, we can classify most of the objects. By the way, just to make sure we're all on the same page, don't mix these representations with the self-attention outputs I just showed you. These are the ultimate representation of the model, which are just some vectors in some space. But the attentions I showed you before are just the output attention map of transformer module, which help us know where the model focuses on before giving us the final representation that we are seeing here. I hope you found DINO interesting so far because now we can talk about it. DINO is not a contrastive learning approach as it is very popular recently for unsupervised domain, and instead it relies on a concept called knowledge distillation. In knowledge distillation, we have a teacher network like ViT large that it has lots of parameters and it performs very well. It is already trained and it is strong but slow. On the other hand, we have a student like ViT base that it doesn't have as many parameters as the teacher. So it is not as strong, but it is faster. So the whole point of knowledge distillation is when we want to train the student, can we do something and transfer some knowledge from the teacher to the student? But we have to do it in a way that it doesn't add any parameters to the student, and we have to keep it as fast as what it is right now. So how we can do it? There are a couple variants outside for this knowledge distillation. One of the simplest ideas is that we add a nil loss function And in addition to penalizing the student when the output is not like the ground truth, we penalize it if the output is not the same as the teacher. So in other words, a student has to imitate the teacher and output the same thing. And as simple as that, we can boost the performance of the student. Now let's just talk about DINO. In DINO, we have an input image, and we perform two different augmentations, which they mainly two different views of an image, and one goes to the student, the other goes to the teacher. And the output representation goes to softmax and gives us some probability scores for different classes. And now you might ask, do we have any classes? Wasn't it an unsupervised method? How do we have classes? You're right. We don't have any labels, but we should have an estimate of how many labels do we have. And if you look at the official implementation of this DINO, you will see this argument that they receive, which is outdim, which is the dimensionality of the DINO head output. And by default, they set it to 65,000. And it is actually a lot, because when we want to train it with ImageNet, we have 1,000 labels, not 65,000. So you might wonder, why do we have that many? Well, that's actually because we have a concept called oversegmentation. By doing this oversegmentation and having more classes, they can kind of classify more than it, like classifying the whiskers of the cat or ears of the cat or, I don't know, nose of the dog or other things that can be done. Anyway, when we have these probability scores, then we can apply our loss functions and distill some knowledge from teacher to student. So as you can see, the orange one is our ground truth that now is the output of the teacher, and it is multiplied by log of the output of the student, so it is a cross entropy loss. But one thing to note here is that teacher is not already trained, and it is training at the same time as the student. So that's one thing. The other thing is teacher is not architecture-wise stronger than student. It has the exact same architecture, exact same number of parameters, but somehow it should be stronger. So there are two questions that you should ask. One is, how can we train this teacher? And the other is, why should teacher be better? So let's just answer this question first. That is because of a concept called multi-crop training. In multi-crop training, when we have an input image, we can perform two different kind of crops. The first one is global views, that we crop more than 50% of the image. The other one is local views, that we crop less than 50% of the image. And the thing is, throughout the training of the DINO, student uses global and local views, but teacher uses only global views. So teacher should generally give us a better representation. Why? Because it receives global views that has more information compared to the local views that a student receives. Obviously, when a student receives global views, it has the potential to output a representation as strong as teacher. But generally, given multiple inputs, teacher should outperform because it always receives global information. I mean the information that is coming from the global views. The next question that we should ask ourselves is, how can we train teacher? Well, the others have tried different ways. Initially, they copied student weights to the teacher during each iteration, and they wound up getting 0.1% of accuracy. So then they tried copying the student weights after each iteration, but it didn't change anything. So they copied the student weights after each epoch, and they got 66.6% of accuracy on ImageNet. But why copying the student weights after each epoch is ideal? Well, I personally think that if we copy the student weights during each iteration and paste it to the teacher, that basically means that our ground truth, which are the output of the teacher, are changing during each iteration. So it's like that the student moves in different direction in each iteration, and it never finds the local optimum. But when we change the teacher weights after each epoch, then we have a stable ground truth for the whole epoch, and hopefully a student moves into a right direction. So the slower we change the teacher weights, the better result we achieve. And that's the reason why they are using momentum at the end, which is this exponential moving average formula that we also see it in the MoCo paper, that the new teacher weights are lambda times the current teacher weights plus 1 minus lambda times the student weights. So this lambda is a value very, very close to 1, and in fact, it follows a cosine schedule from 0.996 to 1, and that basically means we slowly update the teacher weights and get some information from the student weights. And if we look at the validation accuracy throughout epochs, we can see that both teacher and students are evolving. Teacher evolves better because it always receives global information, it has more information, but at the end of the training, both the student and teacher are getting the same performance, and that's when we converge. But why, when we looked at the attentions, it only focused on the objects? The reason is here throughout training that we force a student that has local views to output same representation that teacher gives us, and teacher is also updated based on exponential moving average of a student. So when a student receives a local view of the cat image that has information about whiskers and furs, it should give us the same representation as the teacher that has information of the most of the cat in addition to the background like the tree. So model has no choice other than focusing on the object, because on teacher, if it focuses on the tree, the final representation wouldn't be similar to the student that doesn't have that information. And both the student and teacher must focus on the cat to produce a representation unique to the cat. So the whole reason of this attention we saw earlier is because of these different local and global views. And yeah, that's the whole idea behind DINO. But if you want to try this by yourself and implement it, you would probably fail. And your model actually collapses. And by collapse, I mean your model outputs the same thing regardless of what the input is. So just to know more about this collapse issue, about why it happens and how we can solve it, we should see what this avoiding collapse mean. There are two scenarios of the collapse that might happen. The first thing is the teacher and student might produce a uniform distribution along all dimensions. So regardless of giving an input image of a cat or dog or a building or any other thing, they always output the same thing, a uniform distribution across all the classes. So both teacher and student are the same thing. And that actually reduces the loss function, because on the cross entropy loss, since both the student and teacher are the same thing, it reaches the minimum. But it is not what we want. The other thing is, regardless of what the input is, the output would be dominated by only a single dimension. For example, it always outputs the cat regardless of what the input is. So how can we solve these two issues? Let's just talk about the first one first. So for avoiding producing the uniform distribution along all dimensions, we need to sharpen our output. And how can we make it sharpen? We just need to add one additional term to the softmax formula, which is temperature. So as you can see, this TS or tau S, I don't know how to pronounce it. If we just add it to the softmax formula, it can sharpen the probability distribution at the end. But how? Let me just show it. So let's just assume that this is our logits before going to the softmax. As we can see, they're all almost the same thing. The second one is slightly larger than others, but they're all the same, right? So if we just pass it to the softmax without this temperature term or set it to be 1, this would be something like this, almost a uniform distribution. But if I change the temperature term to a value like 0.1, then even though the second term of the logit was slightly larger, now we can see that it is getting a very, very high probability score compared to the rest. And if I change the temperature to 0.05, then the second term would get a probability score of 0.96, while others are almost zero. So by using this temperature term, I can sharpen my probability scores. So I can add this term to both students and teacher and make them sharpen. But that causes the second issue, which is dominated by one dimension. And how can I avoid this? I can use centering operation, which is when we look at the logits of the teacher, we just add a bias C to it before passing it to softmax. And this C bias term is just some exponential moving average of previous C, which initially was the mean of all the logits of the teacher among all the samples that we have in our batch of images. So hopefully by adding this C term to the teacher, we can smooth out this distribution, and by using that sharpen on both of the student and teacher, we're sharpening both of the outputs, so kinda we just mitigate these two issues. And yeah, that's the whole idea behind DINO, and now we can just talk about the results. So the first result is about image classification. Here in this table, we want to compare DINO with other self-supervised approaches when they all use the same architecture as their backbone, which are ResNet 50 and ViT small. As we can see, when we are using DINO, we are getting 3.5% better in case of using a linear classification after this pre-training. So that basically means that throughout pre-training, we update the backbone weights of the ViT small using that DINO loss that we saw. But after training, we freeze all those weights and then we add a linear classifier on top of it, and we only train that linear classifier. And that way we are getting 77% of accuracy, which is comparable to the supervised counterpart, which is surprising, right? Because in supervised counterpart, we have labels of each image, but now we don't. I mean, throughout the pre-training, we don't. And even though with that fact, we can get a comparable result. And if we are using KNN, then we are getting 7.9% better output compared to the previous state-of-the-art result. And in the second table, we just compare DINO with each model when they are used with their optimal architectures that they was proposed in their paper. And now we can see that when DINO uses vision transformers, it can get like 10 times less parameters compared to the previous state-of-the-art, while being 1.4 times faster and getting a slight better performance both on linear classifier and KNN. And the other thing is about image retrieval, that in image retrieval task, we are having some images of buildings from different views. And if I give the image of that building in one view, can we retrieve the other image from different views? For this task, we are having two data sets. One is Oxford, the other is this Paris one. And when we'll compare DINO with the supervised counterpart, we can see that actually DINO cannot really surpass the supervised counterpart when they both trained on ImageNet. But the good thing about DINO is that it's a self-supervised approach, so I can use a dataset, a bigger one, which is specifically designed for landmarks, which is Google Landmarks version 2. And if I use that for pre-training, then DINO actually can surpass the supervised counterpart and achieve a better performance. The other thing is copy detection. And in copy detection, we have one image, either it is correct image or distorted, and the task is to find the other one, which DINO gets better performance compared to the others, but let's just see how it works. So as you can see, the query image for the first column is just a correct image, and the task is to find the other image, either it is corrupted or just something that is a copy of that, right? And DINO can correctly find the other image, which is kind of distorted by adding the circular image of the other one. But the other architecture, like multigrain architecture or supervised vision transformer, cannot really find a copy. And in other cases, we can see the same thing. For example, at the third column, when we have an image with some distorted text, DINO knows where to focus on. So it doesn't focus on the text, and it can correctly find the actual image. But since the other methods, they do not have that advantage, when we look at the result, they just retrieve some images from some text, and they do not care about the actual image. And the other thing is about video object segmentation that I don't really know much of, but when we compare DINO with other self-supervised methods that they were specifically designed for this video object segmentation, we can see that DINO outperforms that, even though the task is not really related to that. And compared to the supervised approaches, which they specifically designed for video object segmentation, we can see that, yeah, DINO cannot really surpass that, but it is comparable. And that's great because the objective wasn't for the task of video object segmentation, yet somehow it can segment the object by only focusing on the object. And finally, for the transformer learning on downstream tasks, we can see how DINO performs on different datasets for classification and how better it is compared to supervised one. Well, you know how transformer learning works, right? We just pre-train it, but instead of freezing the weights, we just fine-tune it. And this way, DINO can surpass the supervised counterpart. And that's the whole thing I wanted you to know about DINO. If you found this video useful, don't forget to like and subscribe. And until the next video, goodbye.